Hi, today we're going to be looking at Laser Genius, the complete machine code development system. This software package includes an assembler, a monitor, and an analyzer. It came out in 1986. It's published by Ocean, but the software itself was written by Oasis Software. An earlier version of the assembler that comes in this software package came out a few years earlier in a package called Machine Lightning, which was a package focused on video game development. The manual lists 3 names as the authors of the Genius assembler: David Hunter, Martin Lewis, and Andrew Ford. So let's get started. Let's see what comes on the disk. So the programs that we're interested on this disk are GenAsm, the Genius assembler, and when we load that, it's either going to load the ASML or ASMH program. There's GenMon, the Genius monitor, and then there's RelMon, which is a relocating version of GenMon. And then there's the loader. And loader is a program that takes object code created in the assembler and loads it into memory. So let's get started by loading GenAsm. The nice thing is when you load this, it just automatically runs. You don't even have to type run. This is a nifty trick I need to learn how to do because that's really cool. So the first thing it's going to ask you is, do you want to use the low memory version or the high memory version? Well, how do you choose between the two? Well, if you look at this memory map, you really have 2 decisions. You can have the runtime and assembler appear in the lower part of memory between 800 and 47FFX, or the high part of memory at 9000 to CFFF. So if you run the low version, the source code ends up in the higher part of memory between 4800 and CFFF, and if you use the high version, the source code ends up in the low part of memory between 800 and 8999. It doesn't really matter for what we're doing, so we're going to choose the low version. When the software starts, you'll notice the name is C64 MacMon. That's the machine code monitor. This is version 1.5, and the L tells us that it's in low memory. This program appears to be written by David Hunter, and I notice that the other 2 names in the manual are not referenced here. So I can only assume that means that the other 2 developers worked on the monitor and the analyzer. The software first prompts us with the phrase new. Because this is the first time we're loading the software in our current power-up state, it automatically answers yes for us. Now the next question is kind of a mystery. It says text memory. This question is asking you if you want to change the amount of memory that's available for source code, and you can make it smaller than the 34K they provide. So I'm going to press enter here. By pressing enter, the default value of the 34K is what's used. You will notice that we are in resident mode. This means that we are doing all of our source code manipulation and assembly within memory, and we have the option to save that source code to disk later. Disk mode, which we'll talk about later, means that we're doing everything from files on the disk, and that's going to be really useful for really large projects. But for what we're doing, resident mode is going to be more than enough. So looking at the memory map, you're trying to figure out, well, where can I put my program? This is allocated 50K of memory, which is pretty much the vast majority of the Commodore 64. I think I would like to put this program at 8000 hex. So what we're going to do is we're going to restart this and then configure it to use a smaller memory footprint for source code. So we're going to press run, stop, and then restore. So here it's going to ask us if you want to start a new source code project. We're going to say yes. And now this time we're going to configure the memory to use a lot less so we can assemble our code to 8000 hex. So we're going to use hex address 4800, and then you put a comma, and then you put the ending address that we want to make available for source code. And here we're going to use $7FFF. And that's going to give us 14K to play with. And now we have 8000 and up to put our code in. So right now we're in what looks like BASIC, and it is more or less the BASIC editor, but virtually none of the basic commands that you're used to will run here. The only holdover, the most important part that we need from BASIC, is the ability to manage source code using line numbers. So we're going to use line numbers just like BASIC to produce assembly code. Now these line numbers mean nothing in assembly language, and we are just using them to manipulate the source code in memory to move our code around. So let's put some code together and try this out. Commands that start with a dot are called directives. They are not actual machine language code, they're just instructions to the assembler. This particular instruction is .org or origin, and it tells the assembler that when we do assemble machine code and we're going to put it into memory, 8000 hex. So for the first line of actual machine code we're going to write, we're going to start with a command, if you will, called LDA. And this stands for Load Accumulator with Memory. In 6502 assembly language, the vast majority of commands are taking a byte from the 64K of memory on a system and moving it into the CPU, doing something with that value, and then putting it back somewhere in memory. So with LDA, as you can see here, this is a load accumulator with memory. And then the next question is, what byte of memory are we going to load into the accumulator? Well, we're going to type in hashtag $02. We're going to load the byte of memory right next to the instruction, the one that's immediately next to it, hence the name immediate addressing mode, and we're going to put that in the accumulator. So looking at the chart of addressing modes, you can see that A9 is the opcode. So when this assembles to machine language code, it's going to look like this. So the opcode is the very specific addressing mode of the mnemonic, and then O2 in this case is the value we're going to load into the accumulator. And you'll notice in this chart that in total it is 2 bytes long. Well, once we have this value in our accumulator, we want to put it somewhere. So we're going to write it to a memory address $D020, and we're going to use the STA mnemonic to do that. Is store accumulator in memory. So this is going to do the opposite. And if you look at the operation on the note card, there's an A, an arrow, and an M. Anytime you see that arrow in that operation section, you think of the word transfers to. The accumulator is being transferred to memory. So we're going to type in the memory address D020. This is what's called an absolute address because we gave it a literal spot in memory. And the absolute address opcode is 8D. So when it gets turned into machine language code, that's the value that's going to be stored in memory. And then next to it, you might be thinking it's going to be D0 and 20 for the next 2 bytes, but the 6502 architecture is known as little endian, and it actually puts the smaller part of the number first and then a bigger part later. So this is what it would look like when it's assembled. So what is that memory address and why are we putting a byte there? That is the memory address that is exposed by the VIC2 chip, and it's a register, and any value that we write in there will change the border color to that value. And then the last line of our program is going to be RTS, and this mnemonic is return from subroutine. Now you might be thinking, we're not a subroutine, that doesn't make any sense. But when we call our machine language program, it's being called from another program, whether it's BASIC or MacMon here, and when it's done, RTS is going to transfer control back to the program that called it. So that is our first program. So we're going to type list, just like you would in BASIC, and the first thing you're going to notice is that it reformatted our output. Now if we type in the word print, we can see our source code without the line numbers. And again, the line numbers, the only purpose they serve for us is the order in which the lines are displayed on a screen, and we can manipulate those lines and flip them around. So let's assemble this program. We're going to use the ASM command to assemble it, and we're going to pass in "M". What this tells the assembler is take the output, the machine code that's produced by the assembler, and write it to our memory location, which we described as 8000. We've run the assembler, there's no errors, and now our machine code is sitting in 8000 hex. So let's give it a run. We're going to use the sys command to run our program. And of course, our border turns red, so we know our program runs. But let's take a really good close look at this D020 to see what this raw memory looks like. And to do that, we use the mdump command, which stands for memory dump. And we're going to pass in $D020. Now that's kind of interesting. When you look at it, there's an F2 there. I thought we put a 02 there. Interesting. Well, so the memory dump doesn't let us just look at memory. It actually lets us poke values straight into it. So we could put a 6 here, press enter, and a border changes because we just wrote a value straight to memory. So if I were to run this command again, oh my gosh, I could see that it changed my 06 to F6. So what's going on here? So that particular register that's exposed by the VIC chip actually only stores a 4-bit value. Each one of these digits in a hex number represents 4 bits of the 8-bit value. So this side here, where the cursor is the only part that the VIC chip cares about, because it's a 4-bit value, and that holds the numbers between 0 and 15, which is F. hence why we have a 16 color limit. And whatever number you put here is just discarded. The emulator shows me an F here. What I don't know is if on real hardware, this number is random or not. So if anyone has this on real hardware, I'd be really curious to know. Let's make our program just a tiny bit more interesting. So we're going to delete lines 20 and 30, and we're going to use the delete command to do that. So we put 20, 30, and it's going to ask me, are you sure? I'm going to say yes, and those 2 lines of code are gone. We're going to create a loop. And the way to do that is we start with a label. A label is like a friendly name for a line number, but it also keeps track of the memory address of where the next mnemonic. So the code we're going to put in this line is going to be the INC mnemonic. The INC mnemonic is increment memory by 1. And if you look at the operations, it says memory, add 1 to it, and then transfer it back into memory. So we're going to put the absolute address of D020 there. And what this is going to do is it's going to read the value out of that memory, add 1 to it, and put it back in. So this will move the border color of the screen up 1. And then the next line of code, we're going to use the mnemonic JMP. And this mnemonic is jump to new location. Here we're going to enter the label loop, which is going to represent the memory address of the INC mnemonic. And this will cause the CPU to go back the line of code to increment memory by 1. So running this program should make our border colors just change really, really fast and go a little crazy. So let's try that out. We're going to do ASM, M to assemble it. And then we're going to run it with sys 8000. And cool, our border's going crazy. But we're kind of stuck here. It's in an endless loop, and we can't seem to get out of it. So what do? We're going to press run, stop, restore. And you'll notice that our MacMon has reset. Now the question new is even more important than it was a few minutes ago. We don't want to start a new program. We want to continue where we left off. So we're going to choose N for no. So notice now that it came back into the basic editor with the same memory configuration as when we started it. So we have 14K free RAM. And if we type list, our program is still in memory. So with that scary moment out of the way, we should probably save our software because we wouldn't want to lose all this work we've done. The software package has your typical .wedge commands. So if you use an @ sign and then you place a $, you'll get a directory. And here we will see the contents of our disk in drive 8. Now I prepared a blank disk and put it in drive 9 where we can save our source code to, because I don't really want to write our project code to the assembler diskette. So you can change the device that the software uses to drive 9 by using a device command. And now it's going to use drive 9 for all of its disk I/O. So if we issue the $, command again, we'll see our blank disk there. Now I actually have a hard disk, well, a virtual hard disk on drive 10, and we can actually use that too. And the way that the .wedge is written is it's compatible with all the interesting commands of a CMD hard drive. For example, you could see subdirectories there. So I can go into a subdirectory, and you could see a previous project I was working on in a subdirectory. If you're curious how to set up a CMD hard drive in Device, check out my video on it. It's really neat. As you're writing bigger programs, the extra speed and the extra disk space just makes it so much easier to work with. But for now, we're going to go back to device 9. And now we're going to save it to a file called test. So let's change our program to, instead of changing the border colors, to print some text on a screen. Now we're going to write some code that prints the phrase hello world. So let's first by deleting lines 20 to the end. And we can do that with a delete 20 comma command. And we are sure. First thing we're going to do is define a label, a kernel call. So I'm going to use $CHROUT as the label name, and we are going to assign it the memory address FFD2. Looking in the Commodore Programmer's Reference Guide, you'll see that memory address FFD2 is a function called CHROUT, which writes a character to the screen. And all we have to do is put a value in the accumulator, that's going to be the character to print, and then call this. So let's define a block of text to print. So we're going to create another label called text, and this is going to use a new directive called .byte. And this is where we can inject literal text into this memory location when the assembler builds it. And the text is going to be hello world followed by a 13, followed by a 0. 13 is ASCII for the enter key. So when we run this routine through the kernel, it'll print each letter one by one in hello world, a carriage return, enter, and then it will end. So now we're going to create a label called print text. This is just going to be a signal for the part of code that's going to deal with printing hello world to the screen. And instead of LDA, we're going to use LDX. LDX stands for load index X with memory. And like the accumulator, there's an X and a Y register that can hold a single 8-bit value. And we're going to load into this X register a 0. And we're going to use the X register as a variable that's going to index into the string. So when it's 0, we're going to be working the H. When it's 1, we'll be working with the E, and etc. So we need a way to use that to read the memory from our text label into the accumulator one by one. So we're going to start with a label called loop. And this is going to represent a block of code that we're going to loop through. And this time we're going to load the accumulator, and we're going to give it the absolute address of text, and we're going to use a new addressing mode called absolute by X. So and the way you do that is you put comma X. So in this particular addressing mode, we hand it an absolute address, and we tell it that also add X to it. So with X being 0, it's going to be text plus 0 with its H, and then the next time we come through here, it's going to be text plus 1, which will be the E. So the next line of code is going to say BEQ to print done. The goal of this line is when the accumulator has a 0 in it, we're going to jump to a label a little bit later on that indicates we're done printing the text. It's branch on result 0. So there's a set of processor flags on the CPU, and there's 7 of them. And one of them is called the 0 flag. And when the accumulator loads a 0 into it, it will set that flag. And a branch on result 0 will branch to that print done label if the 0 flag was set. And now with the 0 flag not being set, we know it's a character, and we can do a jump to subroutine $CHR out. And of course, jump to subroutine takes an absolute address, but we're passing in a label, and it's going to change that to FFD2 when it gets assembled. The next line of code is INX. Increment the X register by 1. And if you look at the note card here, there's only one addressing mode, which is implied, meaning there's no parameters to pass to it. And now we want to jump to loop, so it can work on the E, the L, the O, etc. And our last line of code here is a label called print done, and that's just going to be an RTS, a return to subroutine. That's our whole program. So let's make sure this assembles with our ASM N command. It assembles perfectly. And let's run it. And if all goes well, we should see hello world. So let's take a look at our source code here. As our program gets larger and larger, and we start working with more than one file, you can easily forget what file you're working on. Now, I know we're working on test, but let's say we're writing a game and we had 10 files, and you're making all these changes, and you're kind of like, oh, I think I'm saving the main file, and you accidentally override it. Well, the Genius Assembler gives you a way to work around that. It's really kind of neat. What you do is make the first line of your code a comment @ and the file name. Technically, @ is a part of the file name. It means rewrite the file name if it exists already. The first line of code is the file name. And where that's used is in the save command. So if I save this now and I use an arrow, the up arrow, the assembler is going to look for that comment to get the file name to save it. So if you get into this habit and saving with the up arrow, it should prevent you from accidentally overwriting a file. And just to show you what it does when a line of code is not there, I'm going to delete the line of code, and we're going to save with the arrow, and you get a file error because it doesn't know what it is. So I'll put that line back in. We'll save it again just to make sure that the line is correctly in. There we go. Fantastic. So now that we have our hello world program, let's make this an actual program that we can run from disk. Let's get some more information about it. So we've been doing ASM, M, which assembles to memory. We're going to add another parameter, L. And this is going to list all of the machine code and memory addresses used during the process. And if you look at the screen, you could see all the bytes we talked about before. You could see how there's between 1 and 3 bytes per instruction. For example, line 80, there's 3 bytes of memory for the jump. You could see that the INX mnemonic has 1 byte, the E8. And you could see each memory address for each part of our code. And you can see, for example, that 8000F is a byte block with the words hello world in it, and then you can see each individual character. But the important thing is our program ends at 801B. So our program is in memory. How do we put it on disk so that we can run it? Well, we're going to use the msave command, the memory save command, to do that. We're going to call A for lack of a better name. Then you pass in the starting address, which we know is 8000, and then you pass in the ending address plus 1. If you don't add 1, it won't save the last address. So we're going to hit save. Now our binary is saved to disk. So let's run it from a reset. And 32768 is what 8000 hex is in decimal. And there's our hello world. It's looking pretty good. Okay, let's pop back into the Genius assembler. All right, we're going to use 4800 to 7FFF to give ourselves 14K to work with in source. We're going to change our device to 9, and we're going to load test. All right, now we're back where we started. So let's take a moment here and really explore how this program runs. And we're going to use the trace feature of the Genius assembler. It's really neat. So before we start with trace, we need to configure it, and you use the opt command to do that. And we're going to pass in 4 parameters. And what these parameters are is J for JSR mode. And what that means is it's not going to step into the subroutines that we call. So that'll make sense when we get to it. Step mode, which means it's going to run 1 command at a time, and we can press enter to go to the next one. Address mode and register mode are just going to show us the current address it's at and the registers for each line of code. Trace is definitely the coolest feature this package has. So now let's type in the command regs. And this is going to show you the state of the CPU. Now there's not too many things going on here. And by the way, this is not the actual state of the CPU right now. It's just the setup for the trace command. So here you can see this is the memory address that it's going to be looking at, which is defaults to 0. This is the contents of the A register, the X register, the Y register, the stack pointer, which we haven't talked about, and these are the processor flags. And remember we talked about the Z, the 0 flag? If that's set, you would see this here. So to trace our program, we need to tell it that we're looking at memory address 8000. So we put an 8 here, we press enter, and if I type in regs again, you'll see that that's how the processor is configured before we start tracing our program. So how do we trace this? Well, you just type in the word trace. And this is a very important step that I forgot. I forgot to assemble to memory. And the default value in memory address 0 was a break command. So let's assemble this. So ASM to memory. And now let's try trace again. Excellent. So what's happened so far? It ran the first line of code, which is load the X index register with a 0. And we can see this is the state of the PC after that instruction ran. This instruction was 2 bytes of memory, so the program counter now is 8002, ready to run the next instruction. And you can see the X register now has a 0 in it. So cool, let's do the next command. We'll just press enter. And the next command was to load the accumulator with the value in text indexed by X. So that was 3 bytes of memory, the mnemonic, then 2 bytes for the memory address. So the program counter is now 8005. You can see the accumulator has the value 48, which is the ASCII value for H, and X is still 0. Press enter again. This is the branch test. Is the Z flag set? And you'll see that it's not set. In fact, if you look at the last instruction, you'll see that by loading the accumulator of the value, it unset the Z flag. So we can press enter to go to the next command. It called the kernel routine to print out the H. And if you look carefully at the end of the JSR line of text there, you can see our H stick in there. And that's the kernel routine printing H out to where the cursor was at the time. So now we're going to press enter again. We're going to increment x by 1. So x goes from 0 to 1. Press enter again. And you'll notice that this is a jump to loop, and a program counter went all the way back up to 8002. And I can keep pressing enter here, and you can see how we're progressing through the program. And eventually, it'll print everything out. So at this point, we don't really need to go through this line by line. To break out of this mode, you can just type in any other command, and now we're not in the trace mode anymore. So let's try a different mode for the trace. So instead of having JSAR, we're going to use JA and R. Oopsie. JA and R. Okay. So we're going to do the same thing, but we're not going to have it stop between each command. So we're going to type in regs again. We're going to reset this to 0. And by the way, another neat thing you can do is you can also set the values of any of these registers to whatever you want. So if you're testing a really interesting piece of code, you can configure everything in just the way you want it before you trace it. Now, if I hit trace now, we turn stepping off, it's just going to run through the entire program until it runs into our RTS. And if you kind of glance at it as it's kind of flying by, you can see the different letters of hello world printing out. Cool, and it's done. That's a whole lot of text. What if you actually wanted to store that somewhere and read it? So we're in an emulator, so we're going to set up a virtual printer so we can see how this function works. So I'm going to go into Preferences and Settings. We're going to go to Peripheral Devices and Printer. We're going to choose File System Access, Enable Virtual Printer, and we're ready to go. And this here is the file name that all printing is going to go to. So we're going to close this. Any command that you type, for example, list, if you put an asterisk in front of it, it'll send it to the printer. So I'm going to open a command prompt in Windows and take a look at that file. So let's use Notepad to see how our output looks. And not too bad. And because we're on Windows and we have a pretty giant display, we're getting this an 80-column output, and it's actually pretty easy to read. Anytime that we print, that file will be appended with the output. Let's run a trace command, except this time to the printer. So let's set this back to 8000. And we're going to do star trace. And before we hit enter, we can watch this print almost in real time. I have a program called tail installed in Windows. Windows doesn't come with this normally, but it's a Linux command or a Unix command to show you a file. And every time something appends to it, it kind of in real time will display it to you. So as we print from the Commodore, we should see it writing to our virtual printer on the screen on our command prompt. So let's give this a try. And there it goes. Cool. So here we can press Control-C, and we can use Notepad to take a look at it. There's our source code at the top. Then here's the trace, and it's showing you every little bit of it. So if you really wanted to debug your code and you wanted to kind of see what's happening line by line, play by play, this is a really cool tool to do that. All right, so let's explore assembling to different memory locations. So if I do an ASM, M, as we've done many times before already, we get the nice successful assembly, no errors. Music to our ears, of course. But let's change the memory address in our code from 8000 to 4800. And we know this is a bad place to put our assembled output because that is where the source code is for our program. So if I assemble this now with ASM, M, it tells me assembly to reserved memory. And that's an error. That's not a statement. It won't assemble it because it knows that that's trying to write into our source code. So it protected itself from corrupting its own memory. However, there's a neat thing you can do in this assembler, and you can actually tell it to assemble it into the reserved area of memory, which is where the source code is, if there's enough room, and run it anyway. And that command is just run like you're in BASIC. So when I run it, it'll actually assemble the code. It's not going to put it at 4800 like the ORG mnemonic says. It's going to assemble it in some space in our allocated 14K of memory and run it from there. So what's nice about this is if you're new to assembler, you don't have to worry about shifting the memory locations around when we boot it up to make your program fit. You can just write your code and run it as long as it's relatively simple code. So that's a really, really neat feature. Typing run does two things at once. It assembles it to a spot in memory that's relatively safe, and it runs it. So it's actually quicker to develop that way. But just be aware that it is assembling not to the memory location in your program. So let's put that back to 8,000 here. So up to this point, we've been doing all of our assembly language in resident mode, and that is where the source code is in memory, we assemble to memory, and we run from memory. Now we're going to explore disk mode. By typing disk, we will switch to disk mode. And if I type in mem again, you'll see that we're in disk mode. So in disk mode, assembly only happens from source files from disk, and then an object file will be written back to disk. The only thing that happens in memory is the actual assembly process. So to highlight that point, if I type in run and I try to run my program, I'll get a can't assemble message. And if I use the ASM command with any options, I'll get a syntax error now. So let's run the assembler from disk. And we do that by typing ASM. Now, because we have a source file in memory, it's giving us a chance to save it out. We don't really care because we've saved it before, so we're just going to press CR, which is character return. Do you want to generate object code? For the first time, we're going to choose no. We want to see the full assembly process run. It's asking us if we would like to generate a listing so we can see the source code and how it is assembled. We're going to choose yes. And it's going to ask us if we want a concordance table. What this is really asking is if you want to see the symbol table after the listing of the code. We're going to choose yes for this. Do you want a hard copy? And what that means is all the output being sent to the printer. We're going to choose no. And the source file name is going to be test. And as we can see, the source code went by the screen, which you've seen before. And at the bottom, we're seeing all of the labels and the memory addresses they resolve to. First, we see it in alphabetical order, and then we see it in numerical order. But at this point, it has not assembled to memory. It just went through the motions of assembling it and giving us the information about it. In order for us to produce code that we can use, we need to assemble to an object file. So we're going to run ASM again. This time, it is not going to ask us to save a file because it already removed it from memory. But this time, we're going to choose yes to generate object code. The source file is still going to be test. And the output file is going to be test.o. And when you generate to an object file, you don't see the listing or anything. It just does it. So let's take a look at the disk and see what it did. So here we could see our test source code, the A, which was the binary we created earlier using msafe, and test.o, which is our object code. Now, a lot of assemblers use the word object code to be the equivalent of writing the program out. The object code in Laser Genius is actually a kind of text file with information in it that makes it easy to relocate. And you need to use what's called a loader to get it into memory. So if we wanted to bring it into memory in the environment we're in now, we use theoload command, which is object load. And if we put the file name in, it loads it into memory, and now we can run it. But let's take a look and use the loader that comes in the software package outside of the editor. So we're going to restart our computer. To load the loader, we're going to load loader, A, 1. And before we answer any questions, we have to switch the disks. The loader software only works in drive 8. So I've just changed the disk. We're going to press enter for the offset. We're going to choose test.o for the file name to read in. And now it's in memory. And you type sys32768, and there's our program. I think there might be a bug in the version that I have here. You'll notice that it leaves the disk drive light on. It doesn't seem to properly close the file, but it does seem to work. With that said, that is how you can load an object file from outside the environment. Let's get back into the laser assembler. Okay, we're going to choose 4800 to 7FFF. And go back to device 9 and load our test program in. So a common thing you're going to do in disk mode is compile multi-file projects. So how do we approach that? Well, first we need to split our test code into 2 files, and make it very easy to do. All we have to do is type in save, the new file name, so we'll call it 1, and the line number range you want to put into that new file. So we can put 10 through 100. So we're going to split the top part of the file into one file and then put the hello world text into another file. So this will save file 1. Oh, whoops. This particular command wants a space between the file name and the first parameter. And then we're going to save into file 2, just line 110. So now we need to make some small changes to the files to link them together. So let's start with the first file, 1. The first change we have to make is let it know that this is no longer test, it is 1. And the way linking works is at the bottom of the first file, you use the file directive, and in single quotes, you put the name of the second file. So when the assembler runs, it will assemble from 10 through 100, and then when it hits that file directive, it'll close this file, and then bring up file 2 and continue from there. So let's save this. Let's load file 2. Interesting point, the quotes are optional on the load and save commands. And we're going to introduce a @:2 here. And then for line 20, we need to put a .n directive. So a .n directive lets the assembler know that this was the last file in the set. You could, of course, also put a file directive instead for a third file, and so on and so on. So let's take a look at this. And then we're going to save this with a caret as well. Now let's run the ASM command on it. So ASM. Oh, we're not in disk mode. So let's type in disk to go to disk mode. Now type in ASM. It's asking us to save text, giving us a last chance to save the file. Well, we already just saved it, so we can press carriage return. We don't want to produce object code this time. I do want to see the listing, and I don't want to see the concordance table, and I don't want to print it. The source file name is 1. That's the first file name. So I paused it with a space bar. What you can see here that's interesting is you can see it assembling the first file, and you'll notice there's a @:2 where the second file starts, and it just continues that missing a beat into the second file. Press space to finish it, and now we've assembled a 2-file project. Okay, let's go back to resident mode, and let's go back to our test file. The last thing we're going to explore is how to create macros. So let's create a macro that simply increases the border color by 1. So we're going to start at line 500, and we're going to choose a label called ink border. And then we're going to use the directive .defcmac. That's the find macro. What a macro is a piece of code or a block of code that anywhere in your program you can just call by name, and it'll just inject those lines of code right at that spot. So here we're going to increment D020. We know what that does. That's going to increment the value in D020 by 1, changing the color from whatever it is to the next color in the cycle. And then line 520, we're going to use the .endMac directive. That's where our macro ends. So how do we call it? So we're going to call this right before the program RTSs, between 90 and 100. So we're going to make a line 95. And the way that you expand a macro or call a macro is you put a colon and the name of the macro, which in our case was ink border. And we can just run this program because that's going to assemble to our source code area and run it just automatically so we can get quick feedback on how well this works. There's a small bug here. Let's list the program and see if we can figure out what went wrong. 95 was a bad place to put it. Let's move our print done label to up here so it includes our call to the border. And then we will run this again. Oops, we forgot to delete it off the previous line, so let's do that here. And now let's run it. And as you can see, it increased the border to black. If I run it again, it'll keep increasing it to the next color. But what if I wanted to set a very specific color? Well, we can do that by modifying the macro to take a parameter. Parameters can be any word you make up. So we're going to make up a word bcolor. So when we call this macro, we can now pass it a parameter, and we'll pass it 2 for red. We're going to add a line of code of 505 to load into the accumulator the bcolor, and then we're going to replace 510 with storing the accumulator at D020. All right. So now looking at our code, where print done is, we're going to call ink border 2, and we're going to pass the color red. That's going to load the number 2 into the accumulator. It's going to store the accumulator into D020, making the border red. So let's run that. And there we go. One minor change we want to make. It is no longer ink border. That seems kind of like a ridiculous name. So why don't we do a search and replace on ink border and change it to set border so the label makes more sense. And we can use the change command to do that. What you do is you pick a delimiter, and we'll use exclamation point, so it's pretty easy. You put the from text, so ink border. You put the delimiter. You put the new name, set border, and then you put the delimiter again. And here it's going to tell you where it changed the name of it. So if we look at our source code now the macro makes more sense. Set border 2. And running this, it runs. So I think this is a good place to end my guided tour of the Laser Genius Assembler package. This is a really nice assembler, and it comes with some really great tools for writing large programs. I found the actual assembler to be lightning fast. And I really like how there's a resident mode and a disk mode. I definitely love the trace feature. That feature is just awesome. And the way that it shows all the status registers at a monitor is great, where it just breaks it out. Most machine language monitors I've played with just show you the number, the 8-bit value, and you have to kind of figure out for yourself which one is the Z flag and kind of do the math on your own. I hope you had as much fun watching this as I had making it, and hopefully I'll see you at the next video. Take care, everyone.